In our earlier discussion of series, we defined the sum of a sequence a little informally. Addition is a binary operation, which means we can only do it with two numbers at a time. This more formal definition respects this fact by defining each term recursively as the sum of exactly two values, the current value and the sum of all the numbers that came before it, which you already calculated. Right, so we can take this a step further and define S sub n to be equal to the nth sum, and then we get a new sequence, which is called the sequence of partial sums. So what I want to do now is prove this statement about a sum, and I'm going to do this using our new recursive definition. So I'm trying to prove something about a sequence. So your first thought when you see something like this should be to see if we can do this using some kind of induction, right? So I'm going to start with this statement here. I'm not going to write it over again. I'm going to start with this statement here as our inductive hypothesis. And when n is 0, this is the sum I equals 1. Our sequence card starts from 1 here, doesn't it? So I should make this 1. Then our sum is the sum from I equals 1 to 1 of a sub I plus b sub I. And that is just a sub 1 plus b sub 1. And those are also the individual sums. The sum I equals 1 to 1 of a sub I plus the sum I equals 1 to 1 of b sub I is also a sub 1 plus b sub 1. That's the base step. All right, so now I need to assume this is true, that this equality is true for n. And what I need to show, I'm going to just put it up here off to the side so we know what our target is. I need to show that the sum from 1 to n plus 1 is the sum of the a sub I plus the sum of the b sub I. All right, so let's see how we can do that. Well, I'm going to start with our definition. Our definition says the sum I equals 1 to m plus 1 of a sub I plus b sub I is a sub n plus 1 plus b sub n plus 1 plus the sum I equals 1 to n of a sub I plus b sub I. Right? That is our new recursive definition. Okay, so what do we know then? But look, our inductive hypothesis says this part is equal to this. All right, so let's rewrite it that way. This is a n plus 1 plus b n plus 1 plus the sum I equals 1 to n a sub I plus the sum I equals 1 to n of b sub I. All right, well, now rearrange them again. Let's put the a's together. This is a n plus 1 plus the sum of the a I from 1 to n plus b n plus 1 plus the sum of the b sub I, again from 1 to n. Okay, now let's apply our recursive definition again. This is the sum I equals 1 to n plus 1 of the a sub I plus, and this part here is the sum I equals 1 to n plus 1 of the b sub I. So this is equal to this, which is what we wanted to show, right? So that finishes the proof. Okay, so now we've seen some basic examples of recursively defined sequences, and we've seen a little bit about what we can do with them theoretically. For example, in the proof that we just did here in this lecture. So what we're going to do in the next lectures, we're going to look at a kind of a bigger example, or we're going to look at a category of recursively defined sequences that are called difference equations.